We'll start.
Yeah, sir. All good. All good. Yeah, we can. Yeah.
Just a minute. Okay. Okay. Yeah. Today is you can
Yeah.
hear me clearly, right?
Yeah. 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 I can hear you.
Okay. So today is about PCB, complete PCB related things and its terminologies.
Mm,
What all
mm.
and its related things. Okay.
Yeah. Yeah.
Since we
Yeah.
have
Okay.
not installed the software yet, we cannot directly jump
Mm.
onto it, and this is also good to understand.
Okay, sir. Yeah.
Okay. Now, what is a PCB? In a very
Okay.
simple sense, it is a
Mm.
specialized platform. This is a platform that mechanically supports and electrically connects components. See, there are so many components here.
Huh.
Okay, so you need to place these components somewhere in order to connect these components, right? So
Yes. Yeah.
this PCB, first of all, it gives a platform to support all this mechanically. It has to support its weight and
Huh.
electrically connects these. So one component to another component, it has to it needs that connection. So that is given by this PCB. Okay, it has
Yeah.
two important aspects.
Mm-hmm.
One is mechanical support,
There is
mechanical,
physical.
yeah, support. Someone else is joining us.
It's me only, sir. I just logged into my laptop.
Oh, okay, fine. Okay, it has to support mechanically, and second one is electrical connections.
Mm-hmm.
And you can see my screen, right?
Yeah. Yeah. It is visible. Yeah.
Ah. So how this PCB is constructed basically, see, you have something called as copper clad laminate, CCL.
See. See. Okay.
Hmm.
Copper quad. Okay. Quad, right?
Clad. Clad means it's in a rectangular form.
Mm-hmm. Okay.
Copper clad
Got
laminate.
it.
Okay. So
Mm-hmm.
because all the conduction thing happens on the copper, okay, it is a this PCB is a combination of conductors and insulators. The copper clad where the conduction happens, and then the
Mm-hmm.
insulators. These are dielectrics.
Okay.
Okay, and
Mm-hmm.
there is no restriction that okay, this copper clad and dielectric has to be in this form only. So you have a dielectric, and then you have on top and on bottom you have copper plates. So this is a dielectric material. On top of it you have a copper sheet which is pressed, and on the bottom also you have a copper sheet which is again pressed with respect to the dielectric. So this is called
Mm-hmm.
as core. Okay, you can see
Mm-hmm.
that core.
Yeah.
It
Yeah.
is
Yeah.
heated,
Core. Yeah.
pressed, and it is called as cured properly. Okay, a
Mm.
cured core means it is
Mm-hmm.
heated and it is pressed with two layers of copper, top and bottom, and it is rigid. There is something called as
Mm-hmm.
pre-preg, pre-impregnated. It means pre-impregnated
Okay.
dielectric. So what does this dielectric do? Is like this acts as a what do you call this glue
Mm.
between this top side of the core copper and then bottom side top side of this core copper, as well as top side of the on the top of that you have another copper plate. So this acts as a glue. This binds these two. Okay. and it is again
Yeah.
it has to be dielectric, otherwise these two will get direct short.
Mm-hmm.
Yes or no?
Yeah. 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 Yeah.
Okay. So this is a four layer PCB. The maximum number of layers so far in a good way achieved is 136 layers.
Okay. Okay. 136 layers. Okay.
Yeah. This is for some power electronics and some
Mm-hmm.
server board. Maybe they have improved up to 206 also so far. I'm not sure, but last time what I heard is like 136 layers.
Mm-hmm.
And it is very thick, like 2 centimeter or so. 2 centimeter or so.
Mm-hmm.
But yeah, now we will not be designing up to this 136 layers. In this course, we will be designing up to 4 layers.
Okay.
Okay. On a special case, we will be designing up to 6 layers.
Okay.
Okay.
So can you add me in the this thing?
Which one?
Uh, I logged into my laptop.
Hmm.
You want to add me
I
in
should
the
add.
this?
Okay. Just a minute. No.
Ah, yeah, got that. Sir.
Okay. Now, this dielectric could be sorry. This especially this prepacked dielectric is of fiberglass and epoxy. These two, it is a composite of these two actually. It provides the insulation to this complete structure on this layer. Okay, this is the conductive layer. This top copper is an etched copper foil. You know what is etched copper foil? Hello, Jawad, you're there? Hello, Jawad, you're there? You're on mute actually. Hello, hello, Jawad, you're there? Yeah. So even though we are doing it, even though these are industrial boards, not only
Hmm.
development boards, industrial boards also, we are doing it only
Mm-hmm.
two-sided because of the lower cost. And also, if it is not complex board, if it is complex board, if it is too much components involved, too much connections, like so much like HDI and those things, you cannot make it in two-sided. I'm telling relatively simple boards. Okay.
Okay. Okay.
Then
Okay. Mm.
comes multi-layer PCBs. So it can count anywhere between like 2 to 20 layers. Okay,
Mm-hmm.
2 to 20 layers. So this is multi-layer. So this is 2 to 20 layers. So where it is used basically for these boards, where complex things are there, like computers, computer motherboards,
Mm-hmm.
computer boards, processor boards, especially
Okay.
processor boards. You know this Raspberry Pi?
Yeah. Yeah. Yeah.
So Raspberry Pi and BeagleBone, these are the processor boards. Those are like between 2 to 20 layers.
Okay. Okay.
And then there is something called as flex and rigid flex. You know flex PCBs. Sorry.
Flex PCB. It will be built in some silicon.
No, 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 no. That is like something. It is, how do I say this? This is like copper, direct copper layers which are embedded on the this one dielectric material.
Paper.
So the rigidity
That.
will not be there.
Okay.
Flex
Okay. So it
PCBs.
is not flexible. It's
It
flexible
is
or it is
flexible.
not
Flexible.
become.
It is
It is
flexible.
flexible.
Okay.
So
It is
not easily
flexible.
break.
No, there is something called
Avoid
as
breaking.
sorry.
Huh. So if it is flexible, so that it is getting avoided from damage or something,
No,
physical
the
damage.
see for anything. Okay, there is something called a stress and strain. You know that, right? For any material, you have certain stress and strain.
Yeah.
Even for this flex
Yeah.
PCBs also, there will be certain amount of stress you can give. You can bend it to certain angle only. Even if you bend it more, it will definitely break.
Oh, okay.
Okay.
So at
So
an
for it,
angle, it is breaking.
sorry.
At certain level of angle, it can't be
Huh.
break
It
to
will
avoid.
not break. And if you press more, if you apply stress more, it will definitely break.
Uh,
For example of this is like watches,
okay.
cameras, and all that. Here it comes, and it generally these flex PCBs are used to connect one board to another board.
Okay. So
Okay.
the costing will be low or high for these types of
No, no,
boards?
no. This is very high. Flex PCB costs are very high,
Mm-hmm.
very high, and this is high.
Okay.
Okay. And when I said that this flex PCBs used to connect from board to board, this becomes rigid because these boards are rigid plus flex because this is flex. So rigid and flex combination
Mm-hmm.
is this rigid flex PCBs,
Okay. Okay. Okay.
rigid flex,
So it will be
and
kind of
this,
thin, right? So the layers
exactly.
might be very less.
Which one? Sorry.
The layers,
Hmm.
so if it is thin, then layers also might be less in this.
Correct.
Then that
In
could
flex
avoid that.
PCBs, you cannot go beyond 6 layers
Okay. Mm.
currently.
Mm-hmm.
Okay.
Okay.
Okay. Now, this is about these layers and all. Now, PCB has
Mm.
got very mainly four type of properties. PCB materials. I am not talking about these copper materials. Copper has its own copper material. What are the properties of copper material?
Uh, Properties, it is conductive
Correct. It
and
is conductivity.
it is it could be easily moldable.
Okay.
Uh,
Properties of copper.
yeah.
Conduction actually. Conductivity.
Uh, yeah.
Condu- Conductivity. And something called as thermal resistance.
Okay. Thermal resistance.
Okay. How much heat
Conductivity.
it
Okay.
dissipates.
Uh, no, sir. Don't have idea.
No, I'll explain. When we come to the designing of these things, I'll explain thermal resistance because we have to
Okay.
design a board wherein you need to calculate how much area is required for
Mm-hmm.
thermal dissipation of heat. Okay, so at that time I'll explain. But properties of copper for the PCB design is mainly conductivity and thermal resistance. Okay, think in these terms.
Okay.
But for
Mm-hmm.
whereas for dielectric I am telling, okay, dielectric
Mm-hmm.
core and prepreg, basically for the core, this is dominant here. Okay, core has got
Okay.
four properties. One is dielectric constant. It is called as dk, and
Dielectric constant. Oh.
huh, another one
Uh,
is dissipation factor df. Okay,
mm-hmm.
this is glass transition temperature, and this is
Mm.
CTE. You know, you must be knowing about this expansion of this. Can you check what is the expansion? Can you tell me what could be the expansion?
CTE, right?
Huh.
CT, thermal expansion, CTE.
You know this expansion actually. I'm really sorry about my handwriting. I hope you're understanding all these things.
No, sir. It's I can understand.
Okay, sorry. Yeah. So this glass transition temperature, I'll tell you, this is like TG. Okay, glass transition temperature. You must be knowing
Mm-hmm.
this thermal expansion, CTE.
Uh, CTE.
I'll give you one hint. See,
Huh.
RT is equal to R naught into 1 plus alpha into delta T. What is this? You know this equation, right? At least.
Uh, P is equal to R naught I plus 2 delta T.
Mm.
No, sir. Can't recall right now.
This is identifying the value of resistance R at
Okay, okay,
certain
okay.
temperature T,
Okay.
RT.
Uh,
Okay.
mm,
R naught is the initial temperature, 1 plus delta T is the difference in temperature. This is coefficient of thermal expansion. Coefficient of coefficient of temperature, right? So this is the
uh,
coefficient of thermal expansion.
okay.
Now you could able to
Coefficient
remember.
of CTE, nothing but in coefficient of thermal expansion,
Hmm.
which are
So if
two.
you open any of the materials, right, material or
Okay.
its data sheet in PCB, say
Mm,
for example this dielectric or yeah, this dielectric or the core, you will have to mainly look into these things: dielectric
okay.
constant, dissipation
Dielectric
factor,
dissipation factor, glass
glass transition
thermal
temperature, hmm, thermal
expansion.
expansion. Okay.
Okay.
Now, what is the significance of dielectric constant? You know what is
So,
dielectric constant, right?
it avoids electricity, uh, so it won't merge with a layer in a PCB. So it divides the kind of mm, copper layer in between PCB.
Where you might have heard about this dielectric constant.
The electric constant.
Hmm.
Mm,
You definitely know about this. Just try to remember where you have heard about this.
the electric constant for uh, in every electronic boards. Mm,
What is this?
Grounding.
Hmm?
This is
A
uh,
capacitor, right?
capacitor. Yeah.
What is the equation for capacitor? Epsilon, epsilon naught into epsilon r into A
Okay.
divided by D. It is the area of the
Mm,
plate divided by distance. And what are these two?
uh, Dielectric constant.
Exactly. So this is the dielectric constant. So see, what is the definition of capacitor? You have two conducting plates. In between you have an insulator. Right or wrong?
Insulation. Yes.
What is this then? You have two conducting plates. In between what you have?
Uh,
Insulator.
insulator plate.
Huh. So that is
Okay.
why you need to know this dielectric constant. Whereas in PCB, so if
Mm,
more the dielectric constant in terms of capacitor, if you have more this dielectric constant, that means it can
mm,
hold more amount of charge without giving certain leakage. That is the definition in capacitor. Whereas in PCBs, what is
mm.
dielectric constant means? It gives the signal propagation velocity. Okay, so velocity
Okay.
of propagation in the signal, sorry, in the PCB depends on this dielectric constant. I will give you propagation of the signals in normal, sorry, in vacuum is speed of light divided by
Mm,
root of this dielectric constant. Okay, so propagation
mm,
in this PCB in any of the signal propagation in this PCB is given by this equation.
mm,
Now, what have you understood? If the dielectric constant is more, the
mm.
signal velocity will be more. That means it takes longer time to go from one point to another point.
The point.
Yes or no? In
Yeah,
the
yeah, yeah.
PCB. So, for lower speed signal, it doesn't affect much. Whereas for high speed signals, it affects significantly. What are high speed signals like USB,
Mm.
PCIe, Ethernet?
Ethernet.
Okay, in these things, this is a very significant factor, dielectric constant. It is very important
Okay.
to know in detail, but it signifies the propagation velocity here. This is one parameter. You have to look in the data sheet of this substrate. These are also called as substrates.
Okay.
Dielectric materials are also called as substrate. Okay. You have to check first thing is dielectric constant. Other one is dissipation factor,
Mm-hmm.
DF.
Mm-hmm.
So, what happens is when the signal is traveling inside this PCB, right?
Mm-hmm.
The signal is traveling from one point to another point inside this PCB. Assume that a signal has
Okay.
a property called frequency, and also, sorry, it has a property of frequency.
Okay.
Just a second. Sometimes I use mouse. This is better actually. So, it has something called as frequency.
Okay.
Frequency, and it will be running at certain speeds, right? That is the velocity of propagation. Okay,
Mm-hmm. Mm-hmm.
so every signal is having certain amount of energy, yes or no?
Yeah, yeah, yeah.
So every signal will be having certain amount of energy. So while it is traveling from one point to another, how much the energy is getting dissipated, or in terms of what is the loss of this energy when the signal is traveling from one point to another point, it is given by the dissipation factor. Okay, it
Okay.
is attenuation or loss.
Mm-hmm.
Hmm. So this is that one, and then something called as glass transition temperature TG. Okay.
Okay.
Now what does
Mm-hmm.
this TG means? You know these PCBs are made up of sand, right?
Yeah, yeah.
Silica, silica sands.
Huh.
I mean these substrate, these dielectric materials are made up of sand. So when you
Fine.
when you when you heat that sand so much, it turns to glass.
Mm.
So it will already be cured and it will already been hardened. Okay, this
Mm-hmm.
substrate. What happens is because of these currents on these tracks and all that, it will get heated up. PCB will get heated up. The temperature
Huh.
at which this substrate turns to glass
Huh. Huh. Huh.
is called as glass transition temperature.
Okay.
At the starting point, not fully glass. The temperature it starts to convert to glass is called as glass transition temperature.
Mm. Okay.
And then the last is coefficient of thermal expansion. I think you already know that if this value is more, that means alpha means, this is also called as alpha. If this value is more means like it will expand more. PCB will expand more in terms of size.
Okay.
So because
Mm-hmm.
of the heat, the glass, it will also go to glass transition temperature, and then the PCB will expand more. What
Expand.
happens?
Yeah.
See, assume that you have a copper clad laminate. Sorry, assume that you have a track on this PCB. So what happens if the PCB expands from here and here? The copper breaks here. Yes or no? The track will break here.
Yeah.
So that's the reason why this is also a very important factor.
Okay.
So these are the four main important things that you have to see when you get a data sheet of the substrate.
The subtract. Okay.
Huh. Now comes the one of the example of all these important parameters. Okay, you have
Okay.
heard about this FR4. It is called as flame retardant 4, category 4.
Mm-hmm.
Flame retardant category 4. Okay, this is a type of substrate. There are multiple categories of this. I exactly have to look into this 4, which is this 4 category, because I don't have
Mm-hmm.
that in my mouth actually, but I'll check and let you know. So if you see
Okay.
this, for this the glass transition temperature is 130 to 140 degrees centigrade. High TG
Mhm.
variant, it has multiple types also. It is like normal as well as high glass transition temperature variant.
Okay.
Just a minute.
Mm-hmm.
And then dielectric constant, it is between 4 to 4.2 to 4.8. Generally we take 4.2. And why I'm telling all this, you will understand once we start designing that. I will
Oh.
seriously show you in terms of simulations and all how these values will affect.
Mm-hmm.
Okay, so and certain at this will almost goes to 4.3 at 1 gigahertz, and then dissipation
Mm.
factor will be like 0.015 to 0.025. Okay, and then
Okay.
CTE. This is in terms of ppm per degree centigrade.
Mm-hmm.
Hmm. Now, this is a these are the four main parameters. Now, if you see this PCB, right, when we know that this will be of certain thickness and the copper will be of certain thickness. So this thickness, there are so many things. You see, you have to balance all these parameters in order to create the thickness of the substrate, thickness of this dielectric.
Okay.
What about this copper? What about this copper?
Mm.
So for copper, you have certain thickness, that is the weight. So for corresponding weight, you have thickness. So for zero point 0.5 ounce, you have 17.5 micrometer. For 1 ounce, 35 micrometer. You have this table. Now,
Okay.
based on what we decide the copper thickness and the copper weight. Any idea?
On its dimension,
What dimension?
if the board is smaller, then we are using the finished copper layer. If the board is quite wider size, and we have to use it kind of more good copper, which can be used in this. If, if you are basically using a bigger boards, you can go for the thickest layer of the copper. Just I'm
Why
guessing.
so? Why not? If we, oh yeah, that's correct. Let us understand. Like you said, if we go for
Mm.
bigger boards, we can go for higher copper weight, right? Why so? Why can't we go
Mm.
for lower copper weight only?
Uh,
Even though the board is bigger.
for its better performance, if you are using a bit thicker layer, it is durable.
Okay.
Um, Yeah. Then.
Okay, we'll try to understand. Assume that this is a trace, okay?
Mm-hmm.
In the copper, in the PCB, this is a small trace. This trace, if you look it from the front side, it looks like this. Okay,
Mm-hmm. Mm-hmm.
so the thickness is 17.5 micrometer. Actually, the trace will not be like this exactly. If you look from the front, it will be like trapezoidal shape. For all our theoretical purpose, we will take square shape. And there is something
Mm-hmm.
called a surface roughness. For high speed designs,
Okay.
when we deal with the high speed designs, I'll explain. So how this copper bonds to this prepreg or dielectric prepreg material, that also impact very much impactful. I'll explain that at that time. So assume that this copper is like 17.5 micrometer, that is one
Mm-hmm.
half ounce of copper. You start sending currents, 1 ampere current you start sending. So it
Mm-hmm.
dissipates certain heat. Okay,
Mm-hmm.
you start sending 2 ampere of current, so it dissipates more heat. If the area of copper is good, okay, you can send more current, sir. Since I cannot increase the area, what I will do, I will increase the thickness. Understood?
Okay. 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 Okay.
So if you want more current carrying capacity is required, then I will
Mm-hmm.
increase the thickness. And
Thickness. Okay.
so in for these are especially used in power electronics applications.
Mm-hmm.
And also I will create an area in such a way that the more amount of heat, because copper is a very good conductor of heat, right? So
Yeah.
the more heat this copper layer will absorb and it will dissipate outside.
Mm-hmm.
So this depends on this one current carrying capacity.
Got it. Okay.
Okay, now,
Mm-hmm.
so uh, in order for any of the PCB to conduct from one layer to another layer, we use bias.
Mm-hmm.
Okay, wait a second. Uh, This is here. Okay, we use something called as bias. You have one copper, one copper here. You have a dielectric material here,
Mm-hmm.
and then you have another copper. These two are conducting.
Mm-hmm.
These two are conducting, and this is dielectric insulation.
Okay.
So, assume that you have one component here and another component here. You started your trace like this. You have to connect from
Mm-hmm.
here to here. You use something called as via. So vias are the one that carries the current from one layer to another layer.
Okay.
You are following me, right?
Yeah. Yeah. Yeah.
Huh. So there are multiple types of vias actually. I will show you. So this is a board. There are multiple types of vias.
Mm-hmm.
You are seeing this. This is the
Okay.
top layer.
Uh-huh.
This is the bottom
Mm-hmm.
layer. You have multiple types of vias. This one will
Okay.
connect direct. This is called as through hole via. So it
Mm-hmm.
punches all the inner layers and it connects directly from top layer to bottom layer.
Okay.
Okay, this is called as micro via, and this is also called as
Okay.
blind via. It connects the top any of the top layers to the next layer, that is the bottom layer. Okay, these are called as blind via,
Mm-hmm.
and these are buried vias. Buried means we cannot see these vias actually in the PCB, but this is still there.
Okay.
Yesterday you asked me a question, right? Can't we able to figure out the schematic from the PCB? You asked
Mm-hmm.
me a question, right? Last time.
Yeah. 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 Yeah.
Huh. Assume that if you can see these wires, it is fine. If you can't see these wires,
You can't. Yeah.
huh, the traceability is still possible. You can use this multimeter to check the continuity and then make that happen. But
Uh,
if you can't see these wires, it is very, very difficult. Yes or no?
yeah, yeah, yeah.
Huh. So this is
Mm-hmm.
through hole. This is blind. This is also called as what do you say? This is also called as blind wires, and these are buried wires, which are hidden, which we cannot see. These are all for the inner layers. Okay,
Mm-hmm.
and then comes something called as microstrip and strip line. So so any trace which is running on top of this PCB, assume that this is a trace. This trace is running
Mm-hmm.
on top of the PCB is called as microstrip, and any trace which is running inside this PCB is called a strip line in very, very simple way. Now you got to know the definition of a microstrip and a strip line. What could be the significance of these two? You tell me.
Micro strip is which we using in uh, lower kind of. It is not kind of very difficult to track, and it also has the faster connectivity with the boards.
Okay, I
Um,
will tell you. See, this is a microstrip. Okay, so it is on the
mm,
outer layer, either top or on bottom. So partially it is exposed to air. Yes
mm,
or no? Whereas strip line,
yeah.
that is the inner layer tracks, it is completely surrounded by the dielectric insulators. Okay.
Okay. Okay.
The question is, we saw that this dielectric constant, the velocity of the propagation is dependent on dielectric constant dk,
Mm, mm,
right?
mm.
So where the signal will be slower, either here or here.
In outer layer, no.
Slower, I'm talking.
In slower.
Mm.
Strip line. Strip line will be slower.
Why?
It is an. It has some. Because it is an internally injected part, and it has some uh, temperature, like dielectric decay. This thing affects in it, and if it is an outer layer and there is no uh, obstacles to stop the signal, so it will be kind of really highly
Mm.
conductive.
Okay. See, what happens is, since this is inside this PCB board, inside this dielectric, right? It has got a
Oh,
single dielectric constant. It is fixed
oh,
5. Okay. So what happens is
mm,
it has a constant, the what do you say, constant dielectric. That's a constant dielectric constant. So because of that,
mm,
it is fixed. Whereas here, one is half of this dielectric is attached to this substrate. Other half is from air. And what is the
mm,
dielectric constant of air? 1.
mm,
So it is all fully surrounded by this substrate. So that's the reason why the signal propagates slower. Another is
mm,
this microstrip. It is partially exposed to this air. I mean
mm,
outside. So the signal will travel faster on this line. Of course, there are certain
okay.
cases wherein we will make these signals travel faster, relatively faster in these inner layers. Even though I
Mm,
told that the signal travel faster on the outer layer microstrip, we still want to route all the high speed signals at the inner layer. not at the
Okay.
outer layer. High speed signals on the inner layer, not at the
Inner
outer layer.
layer.
Huh. There
Hmm.
is a reason for that.
Okay.
So when anywhere, anytime if there is electric field is going, sorry, electric current is going in certain direction, there will be a magnetic field around it. You know that, right? That becomes an
Yes.
electromagnetic
Yes.
radiation.
Electromagnet. Yeah. Yeah. Yeah.
Electromagnetic radiation. So when the signal is traveling faster, the faster the signal travels, the more the radiation.
Radiation. Okay. Hmm.
So what we will do, we will take this radiation and this acts as a shielding. The top and copper layer acts as a shielding. So that means we are containing this radiation inside the PCB itself here. If
Mm-hmm.
there is any
Mm-hmm.
ground path, the radiation will travel to the ground path, and via that it will go to the chassis. That means it is
Mm-hmm.
completely grounded. Here on the
Mm-hmm.
outer layer, the radiation may go to the air. That becomes one EMI issues. That is electromagnetic interference issue.
Mm-hmm.
So if we see any of the faster signals, we will select in such a way that the dielectric constant is lower for this substrate, and we will put those signals we will route those signals in the inner layers.
Okay.
Understood? What is the reason?
Mm-hmm.
So this is another important thing. And then we have something called as HDI, high density interconnect.
Okay. HDI.
HDI PCBs. This one, high density interconnect, is like very the wire drill size is like 0.05 mm, maximum aspect ratio here, standard wire. The aspect ratio means that wire to the pad, okay, and then annular
Okay.
ring. Annular ring is the amount of separation between the wire dia to the solder mask here. That means this much of copper is exposed for the air. If you see any of the
Mm-hmm.
PCBs, you have this um, via, and then you have on top of that you have a copper layer also, so that this much is exposed to the top layer where the from which layer it is connecting. Okay, I will explain once we go to the
Mm-hmm.
design level, design aspects. So HDI
Okay.
design, we are not doing it right now. We just leave it. I just told you. Okay.
Okay.
Now one more thing. When I said HDI, high density interconnector, did you
Uh-huh.
observe? High density means you understood that this is very complex because the more the number of components and more the number of traces. What is this interconnect means?
So just having multiple connections within the buried layer of the PCB.
No, 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 no. Actually, interconnect is an industry standard
Mm-hmm.
name for PCB itself, printed circuit board. We don't say that, okay, we will get this PCB. Interconnect is the word we use in the
Okay.
industry. Okay, because
Okay.
it connects from one point to another point in a very simple way. PCB also does the same. If you
Okay.
apply for this CID, Certified Interconnect Developer, it is not called a
Mm-hmm.
certified PCB developer, it is called a certified interconnect developer. I'll explain that. What is the
Mm-hmm.
certifications and all that? It is called as, in general,
Mm-hmm.
the industry standard name for the PCB is interconnect. Okay? Just keep
Okay.
this in mind.
Yeah.
Now you have understood all the PCB aspects, whatever it is so far I have told. Now let us
Mm.
understand. So for these type of PCBs, like assume that these are the different ways of PCB, different types of PCBs itself, like for embedded boards, power electronic boards, IoT applications, analog boards, digital boards, audio, mixing and RF boards. These are different types of boards depending upon the industry. Okay. Now you tell me what are the significant factors that I have to consider while designing these boards. For example, embedded board. This is a generic one.
Mm-hmm.
So what are the aspects that I should be considering here? Say for example, like normal decay dissipation factor and then dielectric constant or any specific thing I have to consider here. All of them are normal, right?
Uh,
For embedded.
uh, For embedded, so there'll be more. You need to use you're using multiple outer layers to connect for. You'll be having USB, Ethernet, and
That is fine. That is fine. I'm talking these
mm,
material properties.
okay. Uh, so
DK, DF, TG, and then this one CT. Sorry, CT. So I would say for
yeah,
embedded and for mixed signal and for audio boards, I have
DF.
to, I have to consider in a normal way because the
Okay.
signal speeds are low, and then no much other impacts on this TG, CT, and then the temperature rise is also not so high. And for power electronics, I have to consider temperature, TG, and
Temperature.
CTE. So these are
Okay.
dominant one for power electronics. For IoT applications, IoT ports like for
DF.
example your ESP32. Yes, dissipation factor
Mm,
correct, and then
and also the thermal, the TG,
TG
also dissipation factor.
dissipation factor and dielectric constant also because this defines the propagation velocity.
Okay.
Okay, for IoT
Okay.
applications. For analog boards, same we can consider in normal way. Of course, this is like least bothered. Also, temperature wise, because the signal levels are minute here analog boards. For digital boards,
Uh,
also more or less same. Okay, then comes the RF boards. For RF boards, that means the wavelength is very shorter, the frequencies are
mm,
higher, so we have to focus more on dissipation factor and dielectric constant.
okay.
Okay, these are very important things. When before designing the
Okay.
PCB, it is better for you to know
Mm,
this.
okay. Okay. Okay.
Okay, now
Mm,
you can ask me any of the questions if you have on whatever we discussed today.
so- okay.
And one more thing, here
Yeah.
I forgot. See, here on the top you are seeing this silk screen, right? Silk screen is silk screen is something where you write the information on the PCB. You see these white color markings, right? You will write it as U1, R4. These things are called
Yeah.
silk screen layer.
Okay.
So these white and it
Mm-hmm.
whatever the color you want, you can choose. But in general, that is called a silk screen.
Okay.
And
Okay. Okay.
there is something called as solder mask actually. Solder mask is something wherein you have the copper trace, the green color, what you are seeing, the green color
Mm-hmm.
PCB, the green color itself is a solder mask. So it
Green color.
masks the
Okay.
traces from the outside exposure.
Okay.
Okay. So those are also two
And,
important things.
yesterday you asked me to remind you to explain about board bearing of test something.
Which
You
one?
told like board bearing
Bearing.
board bearing of test. Huh. Uh, Bedding or bearing, I did not get that properly, but you asked me to remind you that while explaining about board bedding,
I'm not sure exactly what is that board bedding.
huh,
Okay,
something like that.
no, I'll think of it. That is not board bedding. Probably must be something else. I'll check and come back to you. Okay, not an issue.
Uh,
Yeah. So in on Sunday, actually, I will install this Altium in your PC, and then
mhm.
we will start our designs. Okay. And
Okay,
as
okay.
and whenever required, these theory classes will be there. First theory and then the
Mm,
practical, like how we do um,
mhm.
in our classes, right? In the same way, first you have to understand what you're doing, and then you start doing it.
Yeah, yeah, yeah.
Okay, right? And before we start with respect to this one hardware, like PCB design, we have to understand something called as this standard wise, like IPC triple two one and all that. That there will be
Mm.
another theory class, because it is very important for you to understand at the beginning itself. You have certain idea to design something, and when we come and say that no, that is not how we have to design. This is what is important. Then you should not tell that okay, you should have told us earlier only. Okay.
Okay.
So I'll
Okay.
explain that. Not an issue. So if there are
Uh,
no doubt means we will close for today.
uh,
Please
okay.
check
Yeah.
around say. No
Mm.
worries. See, every parameter in this PCB design is very important. The once you start going to the higher speed, right? Every
Mm.
single thing matters, like the dissipation factor, direct constant, everything matters, and you will be seeing it. So in this course, I cannot give you most of the simulations actually. But when we do the
Mm.
simulations like eye diagram, you know this eye diagram simulation, right?
Uh,
Okay, there is something called as eye diagram, S parameter simulations and all. Those are
mm.
extremely complex simulation, but very important for the high speed designs.
Okay. Okay.
So based on this only, they will tune the PCBs. I will be explaining everything, but I cannot practically do any of the simulations. Okay.
Okay. Is it done in the labs?
Yes, sir.
Uh, do they use certain instruments?
Yes. I will explain that also. How do you get this? Not only simulation. How do you get these measurements done in lab? We use something called as vector network analyzer. Network analyzer, you must be knowing. Smith charts, you must be knowing.
Split chance.
Yeah. So I will explain those in detail, but we cannot do any of the simulations in this class.
Okay.
Hmm. Yeah.
So, do we have oscilloscope and other equipments in the lab in the classes when we come physically?
For PCB design, I don't think that is required. If you are if we are doing any sort of
Okay.
hardware development like embedded hardware design, those are required, and I
Mm.
have all of them. Okay, but for
Oh,
PCB design,
okay.
we'll be designing the board.
Mm-hmm.
So those hardware aspects, I don't think that that is dominant here. Unless and until you have
Okay.
the board in hand, it is not feasible.
Okay.
So you have understood whatever we discussed today, right?
Yeah, sir.
Yeah. You can ask me doubt anytime, not an issue. Just
Mm-hmm.
keep these things in mind.
Mm-hmm.
While designing, these are very important factors.
Okay. So, is the glass transition temperature and thermal expansion.
Hmm.
So, is it both are like? Can you just give me a basic difference between those two? Just like normal basic. So because even the glass transition temperature
Hmm.
and
Coefficient
thermal
of thermal
expansion.
expansion. Yeah.
So,
S-
somewhere
See,
the
in a
both are
PCB,
like
okay. In a PCB, this is as I told you, the substrate is sand, right? So what
uh,
happens is like there will be not every place that you have this thermal heat buildup. So there will be something local
mm,
hotspots where the heat will start building up at that area only. So
mm,
what happens? This glass transition temperature. Assume that whole PCB is not at that temperature, but only this portion is of that temperature. What happens here? The sand will get starts converting into glass TG. Here it will come
okay,
into
okay.
picture. Whereas if you have more number of traces that carrying high current speeds, so uniformly the PCB will get heated up. At that time, this will come into picture. This is coefficient of thermal expansion.
So if it is been if there is a certain temperature that won't damage, or this is the limit of the for the material to have the temperature. So
Huh, huh,
is
huh.
there any limit for the temperature? How do we count or calculate that?
Yes, for
How do we get to
every
know that this
substrate,
is
for every substrate in that data sheet they will mention this glass transition temperature also, and then CTE. You know the CTE calculations, right? RT is equal to R naught into 1 plus alpha T. So you measure that resistance and you will calculate the temperature difference. Or alpha is equal to T2 minus T1 divided
ah,
by
ah,
sorry, I forgot this formula. But you know this alpha is
hmm,
equal to RT2 minus RT1 divided by T2 minus T1 or something is there. I forgot
T2.
that. Hmm.
Okay,
So
no
you
worries.
will calculate. They will calculate the alpha in that way, and you have to calculate the temperature rise for this alpha. Okay.
Ah,
And all these things are given in the data sheet of the substrate material.
hmm,
So that is why when we decide like okay, I need to use this FR4 means I will be knowing that for which type of PCB that I'm designing. Say for example, if I'm designing power electronics, I know that TG and CTs are very important. And if I'm designing generic embedded, I know that TG and CT I can
hmm,
lower it. I can. It's
hmm.
fine. For DF and DK, I need to focus more, and also I have to balance all this because of the costing, because of the cost. The materials are a little bit
Okay.
of costly. As the more the frequencies, the more it gets heated up, the more costlier these are.
Mm-hmm. So in dissipation uh, part,
Hmm.
so we need to have. So is it better that dissipation is lower as much as the
Yes,
dissipation is lower, and
yes, that is the target.
the signal transfer is high?
Yes, that is the target. But the problem is,
Uh-huh.
you know that right? If the length is more, if you route the track length more, what happens? It starts with certain energy and it keep on losing that energy by the time it comes to the receiver.
Okay.
So certain length is also very important. This is very dominant
Mm-hmm.
after 1 gigahertz. Till 1 gigahertz, I think it is fine. But greater than 1 gigahertz, that dissipation factor is very, very important.
Okay. Okay. Mm-hmm.
Signal loss will take place, attenuation that is called as.
Okay.
We will see the
Mm-hmm.
practical example, like how to select a substrate for what applications, considering all this and all that. In like
Mm-hmm.
while going, will you will understand even more. This is just like an introduction.
Okay.
Okay.
Mm-hmm.
Yeah.
Yes, sir.
So next,
Yes.
yeah, you are asking.
No, nothing else.
Yeah. So next on Sunday only we'll meet, right?
Mm, sir. Yeah. So today's, I think
Thursday.
Friday will be the next class. Okay, Thursday. Today is Thursday, Saturday. Okay, Sunday we'll meet you.
So Sunday at 12:30, I'll be coming to the center. Okay,
I'll be there.
fine. And get your laptop. I'll send you the requirement for installing of Altium. Even if you don't install
Ah,
Altium, do not worry. We have KeyCam.
okay.
Okay, do
Yeah.
not worry.
Ah,
Reason is like I said, once you learn one of the car, you can easily jump to another car. Do not worry. Okay, but
okay. Okay.
Altium
Okay.
is
No.
professional version. We will try to install it.
Okay. Okay. So I think I don't have a GPU. GPU is like very minimal, 120.